Okay. So, in this lecture we will continue with what the properties which we had learned with the Laplace transform. Now, we will do the inverse Laplace transform. So, if I can go from t to s, can I come back, and is the transformation unique? What are the properties that are preserved in this transformation going from the s domain to back to the t domain. So, as I mentioned earlier, what we will deal with essentially are causal signals, and therefore, the integration we compute is essentially from 0 minus or 0 to infinity. In that case, the transformation or the inverse Laplace transform tends to be unique. Okay. So, as I said earlier, the inverse Laplace transform helps me to go from the s domain back to the time domain, and there is a reason why we are actually doing this, which will be obvious few slides from now. Okay. So, how do I compute this? If given x of s, the inverse Laplace transform is computed by this formula. L inverse of x of s is 1 over 2 pi j integral e power s t x of s ds, and this L inverse is called the inverse Laplace operator. Okay. Now, one could be tempted to believe that I write any expression in s and there will exist an inverse Laplace transform. Well, that is not true. Inverse Laplace transform, for example, does not exist when x of s equal to s, or even when x of s is s square plus a square by s, for example, or maybe this s may be replaced by a. These are special kind of transforms which we will deal with later, but just to suggest that anything written as a function of s does not necessarily have an equivalent time domain representation. Okay. So, similar to the Laplace transforms, there are also some good properties of the inverse Laplace transforms, right, and then these properties, well, they simplify the process of finding inverse Laplace transforms for complicated looking expressions, right, and this is the one of the usefulness of Laplace transform is also due to the fact that the inverse is most of the times easy to determine, and therefore, we can start from the time domain, go to the s domain, do the computations and come back again to the time domain. Okay. So, back to all these properties which we had learned earlier, they also exist here. The first thing is the linearity property. Say I have two signals in the Laplace domain denoted as x1s, x2s, with their equivalent inverses being x1t and x2t. Now, if I have a combination of these signals, that I have a times x1s plus b times x2s, the inverse of this entire sum would be a times the inverse of x1s, which is x1t, plus b times the inverse of x2s, which is x2t. Okay. So, which means okay, let us do a little example. I want to compute L inverse of a signal which looks like this, 1 over s plus 1 over s plus a, right. So, what I do? I just do because of the linearity property, I compute L inverse of 1 over s plus L inverse of 1 over s plus a, and I know that the L inverse of 1 over s is 1, and this will be 1 over s plus a would be e power minus a t. Okay. So, that is straightforward property. Next, I have the time shifting property, which again was which we had in the transformation from x of t to x of s. So, suppose I have x of s with an inverse of x of t, and now I replace s with s minus s naught, then the equivalent time domain signal would be, of course, x of t would remain as it is, and I have an extra signal e power t multiplied by s naught, which is the shifting in time here. Okay. So, let us take a signal which looks like this, and I want to compute L inverse of s minus a over s minus a square plus omega square, right. So, here I have s shifted by this number a, s minus a over s minus a square plus omega square. So, this could be written as, okay, so if I just look at independently of just how x of t or x of s would look like. So, this is like s over s square plus omega square, right, and with s being transformed to s minus a, this thing looks like this. Okay. So, this means that I can use this property of time shifting, that my signal in the time domain would now just look e power a t. Okay. Now, I know the inverse of this guy, this is my x of s. The inverse Laplace of this guy is simply cos of omega t. Okay. So, I use this very nice beautiful property over here, s minus x 0 would be the original signal plus or multiplied by e power s naught t, where s naught is the amount of the shift here. Okay. Similarly, with time scaling. So, I start with the signal again x of s with an inverse x of t, and I multiply s by a, then the inverse is just given by 1 over a with x, the t now replaced by t over a. Okay. So, let us I can do some example, and these are pretty simple looking examples. 4s square plus 1, this is the inverse of 2s square plus 1, this is almost like s replaced with 2 of s. Okay. So, s replaced with 2 of s, so if I just write down the signal without the time scaling, it will look s square plus 1, again a cosine kind of signal. Okay. So, this will simply be 1 over a. What is a? A here is 2, 1 over 2. Now, this is the inverse of the original signal, cosine of t, now with t replaced by t over 2. Okay. That is a simple way of computing this. Time reversal is very straightforward, x of s goes to x of t, and therefore, x of minus x goes to x of minus t. No need of an example here. Okay. Next is multiplication by s. So, take again the signal x of s with an inverse in time domain being x of t, then s times x of s, the inverse would be, again I start with the signal x and just differentiate it, well assuming that dx, that the initial condition is 0. Okay. So, again a simple nice looking example. I say take a s over s square plus a square. Now, this is inverse Laplace of this signal s multiplied by a over s square plus a square. Okay. So, this is my s, this is my x of s, and this looks very familiar now, right. X of s being a over s square plus a square. What is the equivalent x of t? X of t here is simply sine of a t. Okay. Now going by this one, so x s times x of s would simply be the differentiation of the original signal. So, the inverse Laplace transform of this guy would be d over dt, right. So, this way d over dt of the original signal. What is the original signal? This is sine of a t. Okay. Now, this can be computed to be cos of a t with a. Okay. Now, you go take the Laplace of this and you go back to here, what is inside this bracket here. Okay. Similarly, division by s would give you the integral of it x of s with the equivalent of x of t would be. So, therefore, x of s by s, the inverse Laplace would be this one. So, you see observe that we are actually using these arrows both ways. That means, I can go from here to here and also here to here. Okay. So, well I do not think we need an example, or okay, let us quickly do this. L inverse of 1 over s plus 1, I can write this as L inverse, I have 1 over s, I have 1 over s plus 1, this is looks like this is my x of s, this is 1 over s. Okay. Now, this can now be equivalently written as integral from 0 to t. Now, the original function, okay. So, this should be x, okay. This is so the original signal, okay. Now, look at this guy, this is my original signal x of s, the original signal would therefore be e power minus t. So, I am just integrating from 0 to t e power minus tau d tau, okay, and that will just be 1 minus e power minus t, okay. Now, you can just do the Laplace of this and recover the original signal. Okay. Now, frequency differentiation. So, if I in my Laplace domain differentiate my signal d over ds, that is simply here amounts to multiplying it with a minus t. Okay. Let me do a simple example here. Let us say I have signal x a, okay, just start with x of s is 1 over s, d over ds is minus 1 over s square. Okay. Now, the inverse of this s square is inverse of d over ds of 1 over s. Okay. Now, what is the original signal? X of s going to x of t, that is 1 of s, right, 1 over s, that in the equivalent time domain would just be the unit step, or I will say 1 dot u of t, this multiplied by minus t. So, this will simply be minus t. So, the inverse of minus 1 over x square is, sorry, the inverse of this signal minus 1 over x square is simply minus t. Okay. And similarly with the frequency integration, right. So, I have x of s again going to x of t, the integration s to infinity x of u will again go back to a signal like this. Again I will not do an example for this, but it is straightforward to verify. Once we know step number, the property number 7, 8 is easy to verify. Okay. The other important property is what we learn again in signals is the property of convolution. And why do we do this is essentially because in a control terminology or in a control system, you essentially what we saw in one of our first lectures is I have an input which goes through a system, could be something here on phi, and then I want to measure the output y of t. Okay. Now, this y of t is in some sense some kind of a combination of u t and h t, right, and in signals term this would be is a convolution of u times h. Okay. As the convolution is defined by this property, and this is also commutative h times t convolved with u t. So, convolution is a mathematical way of combining two signals. So, here my input together with the system to get my output of the system, and this is how we will view things in control. So, it is an integral that measures the area overlap of one signal as it is time shifted over the other. We will see a little graphical representation of this. And why is this important for us? Because throughout this course it is important for us to study the response of a system. Response is y of t, the system is h of t for a given input signal, right. So, this is not simply multiplication that u of t times h of t will give me y of t, it is a little more complicated than that. Okay. So, let us see that okay, I have two functions, a rectangular function and g of t is also a rectangular function, and we see how the convolution of these two gives me a triangular signal. Okay. So, let us, okay, I think I hope it will play again. So, this is the video is directly taken from Wikipedia. So, thanks to Wikipedia to make life a little easier for us. So, you see this is one rectangular signal convolving with this red guy, and you see that it is just the yellow one or the area. So, this is the area, this is being computed here. So, this goes and then the area reaches a term maximum here, and then again the yellow line keeps the yellow area keeps decreasing and goes to 0. So, the convolution of a rectangular signal with another rectangular signal is just a triangular wave, the black signal here. Okay. So, So, this actually looks quite complicated, right. If you look at even the expression that I have to actually compute the x of tau, y of t minus tau, d tau and so on to get signals which are the output of those, and this actually becomes too complicated sometimes in doing the integration. Okay. But then when they are transformed into the Laplacian domain, the convolution things becomes very straightforward. Okay. So, what does the convolution theorem say? So, if I have a signal in time domain x of t and I want to see its convolution with another signal y of t, it just becomes a simple multiplication of their individual Laplace transforms. So, the convolution of x of t with y of t is just a very simple multiplication of x of s and y of s. So, therefore, if I now look at it in terms of control, what I had written earlier, that I had a u of t here, I had a h of t and I had a y of t here, right. So, my y of t which earlier was h of t convolved with u of t, now I can write this simply as y of s is some h of s times u of s, as simple as that. So, convolution becomes a very simple multiplication or a product, and this actually helps now to solve lots of problems, right. So, if I want to see how this signal looks in the time domain given u t and h t, I first go to the Laplacian domain, I compute h, I compute u, I do the multiplication, and now y of t can be easily computed as the L inverse of h of s times u of s. These tricks we know how to compute, right, with several properties, and therefore, studying convolution becomes a very easy property just by multiplication and the inverse Laplace transform. Okay. So, as an example, right. So, I want to find the convolution of a signal t u of t with sin t u of t. This is like the unit step, right. This is like t and t. So, x of t is sin t u of t and y of t is t times u of t. If I just go by the formula x times y going from minus infinity, okay, this will x of tau y t minus tau d tau, I just substitute for each of the signals, and since okay u of t is the unit step starting at t equal to 0, I need to compute this kind of complicated looking integral, right. Instead what I could do is I can just go to the Laplace domain or the S domain, where I compute the Laplace of sin of t times u t, that is this guy, plus y, this t sin of t would be 1 over s square plus 1, Laplace transform of t would be 1 over s square, and I can write this as sum of these two Laplace transforms. And I know now that the inverse of 1 over x square is t and the inverse of 1 over s square plus 1 is sin of t. So, the inverse of, so the convolution x with y in the time domain simply looks like this, and I do not have to go through this complex process of computing this integral. Okay. So, one advantage we saw so far is that the Laplace transform easily helps us in computing the convolution, where convolution is just a multiplication. Second advantage is in solving ordinary differential equations. So, solving an ODE in the S domain is much simpler because, okay, so let us see this little example. So, I have this example d2x by dt square plus twice dx by dt minus 1, this is my differential equation, maybe this is equated to 0 on the right hand side. Okay. So, now what does this expression become? Well, this expression on the right hand side becomes, by using those formula for differentiation, s square, this will be 2s minus 1 all multiplied with x of s. Well, this is under the assumption, well, we just make it for simplicity that the initial conditions all are 0. So, a differential equation here is now transformed to a linear equation. I know very well how to solve linear equations, and this Laplace transform is applicable to lots of signals, continuous signals, piecewise continuous, periodic, step and impulse functions. Yes.
That has to be minus x of t, t square x by dt square plus 2 dx by dt minus x of t.
Okay, okay, okay. So, this little question that this should be actually be minus x of t. So, this x of t transforms via L to x of s. Okay, yeah, thanks for pointing out. So, d2x by dt square transforms to s square times x of s with the initial conditions being 0, 2 dx by dt transforms to 2 times s of xs, and x of t simply transforms to x of s. So, this should actually be a x t here. Okay. Thanks for pointing that out. Okay. So, this transformation from a differential equation to a linear equations would make computations very easy. And we also know, so if I determine x of s from this, like equating this to 0, and I can then find what is x of t is simply the inverse of x of s. Okay. Okay, so let us see how we could do that. So, let us consider a simple RLC circuit. So, I have a voltage source, I have a resistor, inductor and a capacitor, and let us say all initial conditions are at 0, and V is simply a unit step, and for computational purposes we will assume that R is 2, L is 1 and C is 1. Okay. So, first thing I would know is, well, I just apply KVL to get this dynamics of the system, right. So, Vt is Ri plus L di by dt plus 1 over C integral I dt. Right. Now, the Laplace transform V transforms to V of s, I transforms to I of s, the differentiation of I would multiply it by s with I of s, the L remaining as it is, and with some initial conditions which are assumed to be 0, and we will see that this guy also eventually will go to 0, because the inductor does not allow a rapid change in current. And then the integral property, right, integral of I dt would be I of s over s with the C remaining as it is. Okay. So, the current, if I were to solve for the current would be I of s is V of s over R plus SL plus 1 over SC. Right. Just this differential equation now transforms to a very nice linear equation over here. Okay. Okay. So, let us try to find out how the solutions look like for these values. So, I have R plus SL plus 1 over SC. I substitute values. U of t is a unit step, V of t is a unit step, therefore, V of s is 1 over s, and for values of R, L and C, okay, I think this should correspond to R equal to 2, right. R equal to 2 would be 1 over s and all these expressions, and I just write this to be I of s is 1 over s plus 1 square. And now, I have this in the Laplacian form, I can easily compute what is the time equivalent of that. The time equivalent of that is the inverse of this guy, Laplacian form inverse of 1 over s plus 1 whole square, and I can use the properties of my inverse Laplace transforms to just get that the signal in the time domain is just t e power minus t, which is the solution which I am looking for, right. So, this differential equation or the dynamics initially were differential equations. Here I convert that into a linear equation to get an expression for the current in the S domain, and I do the inverse Laplace to get the expression in the time domain. Okay. Now, I will do some other example with some non-zero initial conditions. Y double dot minus 2 y dot minus 8 y is 0, y at 0 is 3 and y dot at 0 is 6. Okay. So, the first step would be to write this equation in the Laplace domain. So, this would be s square y of s minus s y at 0 minus y dot 0, again with the second term 2 s y of s minus y of 0, and the third term minus 8 y of s is 0. So, this would mean that y of s could be written just in terms of a expression in s like this, 3s over s square minus 2s minus 8, or just the denominator could be written as a product of two of these terms, s minus 4 and s plus 2. Okay. So, applying the rule of partial fractions, which we would have learned while dealing with solutions of equations, I can write y of s as composition of two signals now, 2 over s minus 4, 1 over s plus 2, and I can now easily do the inverse Laplace to find out that the inverse of 2 over s 1 over s minus 4 plus the inverse of 1 over s plus 2 gives me the following expression for y. right. So, again the process is becomes very straightforward. I am just now solving for linear equations in the S domain, and then I am applying the inverse Laplace transform to get the solutions to equations, right. Okay. So, to summarize, what we have learned in this lecture is inverse Laplace transforms and its properties, a very beautiful property of convolution, where the convolution just translates now into a very simple multiplication in the S domain, and solving of ODEs using Laplace transforms. In the coming lecture, what we will look at is to write down system or a given set of equations as a transfer function and then explore its properties. We will try to do stability analysis, its response to various kinds of signals and so on. That will be in the coming lectures. Thank you.